Hello everyone, today I'm going to explain you one part of the lecture that I didn't explain in the details while doing the lecture. So it is about the Lineweaver Burk plot and how they got this plot. So I was telling you that it is actually about the ratio between the constant of Michaelis and the maximal speed. Okay, so what do we have here? We have the usual formula, which is the rate of the reaction at any given time would be equal to Vmax times the concentration of the substrate divided by the constant of Michaelis plus the concentration of the substrate. So what they did, they took a reciprocal of this formula, so they turned it as 1 over V0 would be equal to constant Michaelis plus substrate concentration divided by Vmax times S. Okay, so we have this formula now, and we can actually divide this part and this part by this divisor. And what we get, we have constant of Michaelis divided by Vmax times substrate plus 1 over Vmax. Okay, so what we have here, we actually have here the linear representation of our graph. Y equal to ax plus b. So here you have the y, then you have the ax and plus b. Okay, so what do you need to understand here is that based on these calculations, you could always find your constant Michaelis and Vmax from this graph, and they would be equal to, in one case when we have this part equal to 0. So when do we have this part equal to 0 is when this part is equal to 0 too. So in this case we want to remove this ax, and x should be equal to 0. And then y would be equal to our b. In this case we have b as our 1 over Vmax equal to the value of our y-axis. So this y-axis when we have x equal to 0. So for example, for this particular graph, it is about 0, 0, 0, 0, 25. Okay, so what would be the real meaning of this Vmax? It would be equal to 1 over 0, 0, 0, 0, 25. And it is equal to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 divided by 25, so it is 4,000. 4,000 of nanomoles per minute. Okay, so we've got our Vmax. To find the constant Michaelis, we need to tie it to our x-axis. And in this case, you see that x-axis represents the 1 over concentration. So 1 over some kind of concentration at the point when our graph intersects this axis. So let's call this point here 1 over C0, and it would be equal to minus 1 over constant Michaelis. So this part would be equal to 1, so let's call this 0, 2, so it would be equal to minus 0, 21-ish. And of course it is divided by nanomoles. Okay, so what we have here, we have minuses on both sides. So let's write it like this, equal to minus 0.21 over nanomole. And we just move it to the other sides so that we obtain the constant Michaelis in nanomoles. So 1 nanomole goes here, and 0.21 goes into the place of Km. So Km would be equal to minus 1 nanomole divided by minus 0.21. Of course, these minuses, they cancel each other, and we are left with about 1, 2, 1, 2, so it's about 4.9-ish, or a little less than that, nanomoles. So it is our constant Michaelis. So these are the ways to find the crucial parts for our enzyme kinetics. So it's constant Michaelis and the Vmax. So to find the constant, we need to take the intersection with our x-axis, and to find the Vmax, we need to take the intersection of our graph with the y-axis. So I hope it was clear. So the mathematical part of this graph is actually very easy. So if you have questions, please let me know. I will see you tomorrow because we have proctoring during the exam. And the exam is going to be 7 to 9 p.m. Because some people are having other classes, etc. So we want everyone to log in and have their exam in a smooth way. Goodbye.